let's continue with question 2 from the exam. So let me pull up the solutions and exam doc in case you don't remember where that is. Yeah. Background, I should also double check to make sure there weren't any questions submitted. Sometimes I forget to check the Google form. Don't get too many submissions on it. Nor do I get notifications. Oddly enough, it's not an inbuilt thing. Oh shit, maybe there was. Okay. Yeah, sure. Probably finish this sequence of questions for question 2, and then we'll pop into those. How's that sound?
Sounds good.
Actually, these do look more complicated. Maybe we should start with them. Yeah, because this sort of stuff's going to be whatever. I'd rather we get through something you're actually looking to get an answer for. Let's do that instead. Okay, evaluate some definite integrals. I'm assuming these came from Tech Free.
Yeah, the tech free.
Yeah, okay. Cool. All right, well, they are certainly on the challenging side. Evaluate definite integral, 0 to natural log 2, 4e, all of that. Yeah, so the challenge is just going to be... This one shouldn't be so bad, because both of these do show up on the formula sheet, as far as getting capital F of x, the antidiff. And then shoving in the natural log, I can sort of picture ahead of time. There's going to be something in there with the like e to the power of natural log. Those cancel down. And so, yeah, let's see how we go with it. So, got the integral of 0 natural log 2 4e to x minus 3 on 1 plus 2x. And so capital F of x. Well, we've got to now antidiff both of these. Did you have any trouble antidiffing these?
I kind of just like this was just like sort of like a addition, like an additional question because there were these three series of questions
Mm.
that I just looked at and like they looked like really hard. I didn't really attempt them.
Oh, sure. Okay. Well, let's see how far we can get then. Antidiffing this. What do you think is going to be? The 4e2x is definitely the easier of the two to antidiff. Yeah, ideally you do those one at a time.
2e to the power of 2x.
2e2x, yeah, because you're just dividing by that coefficient. Yep. 2e2x. And then this one's probably the bit more challenging one. See how you go with it first before I give any particular advice.
-3 on 2, natural log 2x plus 1, but I
Hmm.
don't know if they haven't specified if what x's value is.
You're right. Yeah, there's no
We put the absolute brackets around it?
the challenge there is that absolute value isn't in method study design, which is why every common question that comes up will say x greater than zero. Typically, it's always x greater than zero. Actually, do you know what exam this came from?
No, this is just some like study material I got from a
Oh,
website.
sure. I mean, it certainly looks like a an exam question style. Um, yeah, there probably should be some sort of x greater than zero statement in there. You can put the absolute value signs if you want in there. That's very safe, but I will say it's not method study design material. Um, it shouldn't matter, though, I suppose. We are working with purely positive numbers anyway. But yeah. Yeah, and then just, well, capital F of top minus capital F of bottom. So capital F of natural log 2 minus capital F 0. Again, probably using different sets of brackets to make it easier to see what's what. I typically will use square brackets for each of the individual terms. So capital F of natural log 2, we're looking at 2e2 bracket natural log, well, maybe not even do a bracket. 2e2 natural log 2 minus 3 on 2 natural log at natural log. Really? Yeah, okay. Natural log of 2 natural log 2 plus 1. And that's the first one, minus capital F0. So we're looking at 2e to the 0, so just 2. And then natural log 1's also 0. So that's, yeah, because you're shoving a 0 in there, natural log 1. Yeah, okay. So, now to simplify from here. There's a specific rule that we can use to simplify this one. Any ideas?
I'm not for sure, but I think like the exponential and the log usually cancel out.
Yeah, we do have to do a bit of pre-processing on it to make it
Oh,
happen.
hold up, the two in front of the log,
Hmm.
does that become the power
Sure
inside the
does.
bracket? So it become natural log 4.
Yeah, 2e natural log 4, and then because you got base of exponential and base of log are identical in the power system, um, now you're just left with 4 at the front. So 2 times 4, 8. Now here's the really weird one. 3 on 2, natural log of, I guess we can do the same thing here, natural log of 4 plus 1. That would be a start. And then minus 2, well, whatever. Just making sure the brackets are good there. That one's 8, that one's normal, and that one's, yeah. 6 minus 3 on, well, do I want to do a 3 on 2 here anymore? Maybe we want to put it in the thing. Well, maybe this is just natural log 4 plus 1.
Is it possible to like do a natural log of a natural log, or
Should
because
be.
I've never seen that.
Yeah, no, neither have I, but this is just a number. Like natural log of 4 is just some decimal. Um,
Maybe
you could
maybe
probably,
not.
well,
Then
yeah, you
maybe
could
it's tech active. I don't know.
say again.
Then maybe it's tech active. That's like, yeah, it's kind of
Well,
hard.
if it's tech active, then you just plug and play. I can't imagine it being tech active. I'll just quickly double check just to make sure. Like, if I do natural log of natural log, probably doesn't simplify much. So, um, We'll go ln 4. Yeah, doesn't. There's no like mathematical algebra sort of stuff to go ahead and do. In fact, we can doubly make sure to see, hey, what does the CAS give us? And I think that's pretty much going to be what it is. Like maybe you can shove the 3/2 in there as a power. Maybe you can split it up with the power with the product. Well, not even product actually, because it's pluses in there. Um, yeah, not a whole lot that I can see that would be simplifiable. Let's just double check to make sure there's nothing that I've missed. 42x minus 3 on 1 plus 2x. X. Yeah, it's the same thing. So there wasn't any further exponential slash logarithm conversions to be done there. You pretty much just leave it as a, you have to sort of trust that the nasty number is also correct. Fair enough?
Yeah.
Cool. Moving on to the next one. Okay. Integral from 1 to 2 of a big separate set of division of functions. Does give us a hint. What's the derivative of 1 over f of x?
I feel like I would be able to do it like by dividing like the factors and stuff, but I don't understand like what the like relation is with one on f of x.
It's possibly a integration by recognition thing because we don't know how to do integral of division of functions, basically. And so it could be that when you do your diff of 1 over f, you say, oh, cool, diff of 1 over f equals this, therefore integral of both sides, and then you do that whole integration by recognition thing. So let's see where that takes us. So if we have diff of 1 over x, so d dx of 1 over f, that's just the, well, that's f to the power negative 1. That's just a log, isn't it? Always get it back to front when it's 1 over x on logs. Let me just double check. Nah, it's integral of 1 over x is log, so diff of it is just, you got f power negative 1, negative f to the power negative 2. So dy dx negative 1 on f of x power 2. And that is basically what we, a very similar thing to what we have here anyway, where you could imagine f would be the whole quadratic on the bottom. Oh wait, no, this is chain rule, because you also got to do derivative inner. So, I mean, when you have x, this is what that is, but when it's like f of g of x, for instance, there's chain rule elements to it. In fact, looking at it now, yeah, if you look at the proportion between the actual function that we have, it's derivative on top and original function on bottom. And so rather than what's derivative of 1 over f, probably should have said something to the effect of what's derivative of 1 over f of g of x. Maybe. Hmm. But yeah, basically we have derivative on top and original on bottom. G dash on, is it f dash? What's the actual notation for this? There's a specific, let me pull it up, a specific sort of chain rule thing for the log diff. Oh, sorry, not the log diff, the 1 over x diff. Let me grab that. Calculus, derivative techniques. Yeah, so it's this. You have g to the power of n, where in this case our n is -1. Power goes out the front, whatever. So that's why we had the negative there. G dash has also got to go there. So I guess to amend what the thing should have been, you've now got f dash up here. So it's negative f dash over f of x squared. And so integrating both of this. What's the actual? Let's pull the actual question back up. Yep. So integrating this scenario, I guess you just sort of take the negative out so it looks similar. So we go integral of that equals integral of that. Y, the original function. So I guess you'd call that f of that's y. Derivative of y is that. That's our y. And then you've got your integral of, you could even put the negative out the front. F dash x over fx squared. 1 over f of x is the integral of that. Bring the negative over again, over there. Sure, you've got terminals, but we'll get to that later. This right now is what we're trying to do, because f is the whole quadratic, f dash is the 6x plus 5. You can see how those sort of combine into each other. And so using the integration by recognition, the capital F of x antidiff of this is that. So you just need to know what's f. And if you look at the way the notation is written, f is the denominator without the square on it. So our capital F of x in this scenario, -1 on 3x squared plus 5x plus 1. That's a really nice question you brought to me. And the rest of it's just whatever. Sub in your 1 and 2, and then you're done. That was a really cool one. Yeah. Nice work finding that. The hint there was very necessary, because it gets you to think about, oh, derivative, integral, cool. It's going to be some sort of integration by recognition type approach to it.
Chris, for some reason, I just saw your method and it looks cool. Like I think it's right, but when I put into the CAS, it gives me natural log of the quadratic on the bottom.
Natural log of the quadratic on the bottom. Uh,
Oh wait, hold on. Let me see if I've. Oh, I forgot the square on the bottom. Hold on.
yeah, okay. I'll do it too, just so we can all look at the same thing.
Oh yeah, no, no, yeah,
It turned out fine?
yeah,
Yeah, okay, cool. Yeah, because if I started chucking natural logs in there, I was going to be very confused.
yeah.
I can imagine the natural log being in there because it becomes, you got linear divided by quadratic becomes linear. So you've got 1 over a linear. That's the natural log thing.
I've never seen a question like this before. Like I've seen like ones with like where they give you a derivative, but not
Mm.
like they ask you first find the derivative and
Yeah.
then.
Well, I mean, you have technically. Like the very first time this shows up is in the textbook, and it says find diff, hence find integral. So you technically have done it, but the way it's phrased as a hint is a bit different than if it's like, hey, actually, like do this, do this. And so yeah, it's technically stuff we've done before, but you can see how just the sort of generic nature of it is a bit more tougher to spot. You have to first identify, yep, the hint's going to be important. I should actually find the derivative, not just sort of imagine it. you have to then compare that to the integral that you're seeing and realize, oh, I do actually have the derivative on top of the original function. 6x plus 5 is related to the 3x squared stuff. Those would be the main things to spot, I suppose. And then from there, it's just a bit of integration by recognition algebra. Good question. And then sec squared, I mean, whatever, that's probably
Tan, right?
special, but sec squared is 1 over cos squared. So you can now just replace that with 1 over cos squared. Oh, sorry, no, hang on. Sec squared 1 over tan?
Yeah, I thought like when you integrate sec squared, it becomes tan.
Yeah, because that's the if we pull up a formula sheet, that's testing me now. What's the yeah, so diff of tan is sec, so integral of sec should go to tan. Yeah, okay. Yeah, that's right. Cool. So integrating this then, this is going to be very similar to the part A, or the first question we had a look at, which is you go to each term individually. The only difference is that this one isn't explicitly on your formula sheet under integration. It's under the calculus, the diff tab. So if I pull that up on the screen share properly, you'd now just be looking on this side to spot that. But yeah, you've already spotted that. You said yourself. Integral of sec squared gets you to tan. Um,
Right. Like my problem is not really with the like what the integrals of the actual like trigonometric function is, but more so like you know the like how there's translations in there. Like how do
yeah,
you handle those when you're integrating, or do they just not play a factor because they're
yeah,
trans?
true. Okay.
'Cause I've never like
Um,
really seen that before. That's what I want to know.
yeah, how do we handle the translation element as far as integrals go? Well, it is tan. Oh, hang on, no, it's sec squared plus pi. Because I'm thinking your plus pi in there, that's a pretty, like, under tan circumstances, that disappears. Because whenever you plus or minus pi, you get to the exact same spot, tan wise. I don't really know how that plays with sec squared in particular, though. Let's have a think. Sec squared x plus pi. Well, sec squared is one on. Well, we can probably figure this out. So the integral gets you to tan, sure, but maybe we need to play with it a bit before the integral. So sec squared is the same thing as 1 on cos squared. So you've now got a half cos squared x plus pi. Here's a rule for cos x plus pi. If we think about unit circle, some base angle, plus pi always flips it to whatever. So let's say it's some positive, plus pi is going to make it negative and vice versa, but because you're squaring it, it cancels down. I think that's right. Let me just run that logic through my head one more time. Cos is some x coordinate, so plus pi would shift it horizontally. So if it starts here, it ends up there. If it starts here, it ends up there. Here, there, yeah, cool. So it always flips the sign, but stays the value. Yeah, so this is just cos squared x. And so there's no actual plus pi in there. I'll get the CAS to quickly verify that. Cos x plus pi squared. Yeah, cos squared x. So you're playing with a bit of symmetry stuff in there was the key, because as you're absolutely right, when you do an anti-diff like that, like let's say for instance we did it on sine, just the anti-diff of, I don't know, let's just call it 1 on sine. Sine x plus pi, because that won't have an easy thing. At least I don't think it does. You can see it does all sorts of, well, it did disappear in that case. Let's see. If we get rid of this, does it? Point is, anti-diffing when you have stuff in there, like translations in there, does impact it. I just can't seem to think of a good example to show. And so playing with it before doing your anti-diff to try and remove it would be ideal. I have also noticed there's one in the cos as well. That one might not be as bad. Anti-diff of cos. Well, no, they did do anti-diff of cos AX. Does it always just disappear? Because it
I
is a
just
kind of...
I just did like a generic one like sine x plus pi,
Yeah.
and when you integrated it, it became cos x. Like I don't know if that's the case for every single one of them, but so far it looks like every time the translation just disappears.
Yeah, let me follow this up like a bit more formally. I've got a thing that I didn't think would be super helpful, but apparently it will come in handy now. Rules for integration. There's this special thing that you can do called what I forget what it's called. It's been so long. Integration by substitution. So this is where you can now, like, where is it? Oh, Appendix 2. I thought I deleted it for some reason. This is where you can now handle these sorts of things. So let's see what happens. For this one, you just keep the function as is and treat it like normal. The exponential, this is screen sharing, yeah? Yeah. For exponential, yeah, still just going to come out as if the translation didn't matter. Yeah, okay. So, yeah, it's going to be the case where your translation doesn't actually end up playing a role, oddly enough. And I guess part of the reason why is because you've got to do this sort of du dx sort of thing. You're kind of doing chain rule, where you take whatever the chain rule or composite function portion of the function is, and make that equal to your u, and then what you're essentially doing is converting your entire integral from in terms of dx into purely in terms of du, or just u. But converting from x to u, that's pretty chill. You just slap the u in there and that's whatever. But dx to du, you now have to do some sort of diff magic where you create your u, du dx, and then rearrange it as if it's a fraction. And so now you have, oh, here's dx. I'm going to replace my dx with the version of du. And because it's linear, that term will always disappear. So when you go and plug it into your integral, it disappears. Yeah, cool. Didn't think that would come in too much handy, but apparently has. Um, yeah. So I guess all in all, that wouldn't have, yeah, that plus 2 pi on 3 or whatever it was is not actually playing a role. Oh, yeah, plus pi over 3 doesn't actually play a role in that thing. Where'd you say you found these?
So a while back, my friend sent me this website called VCE Bricks.
You see bricks. Yeah.
Yeah, I'm not exactly sure how legal that website is, but I mean there's just like good content there for like
Yeah, yeah,
revision.
yeah. It's the file server stuff where people upload past exams and study resources from other companies and stuff.
Yeah.
ATAR, there used to be ATAR Rocks, that went down. VCA Rocks, that went down. Um, Similar stuff like that, yeah. These are, I mean, if they're methods, they're definitely higher end methods because I've had to bring up two special things to talk about it.
Yeah.
Um, but but yeah, there were. I guess you can see some sort of inroads in the way towards getting there in a methods-like way, but it's kind of cheeky the way they've done it.
Yeah, I don't know, like I was playing around with the translations on the CAS as well. Like sometimes the translation disappears, sometimes it's there, like
Oh well, I mean, yeah. So the rule is as I've basically just described it here. It's I'll drop this entire doc in here if you want to read up on it specifically. You're following this procedure. It, I mean, it does work with non-linear stuff as well in there, but you have to play a lot harder with it. I've only done it with linear because, well, for starters, it's special as is. Um, but yeah, if you want to explore as to why sometimes it disappears and sometimes it doesn't, like you can see here, you got your AX plus B where it otherwise may or may not have stayed. Um, this one will at the very least explain how this formula sheet thing came to be. But yeah, if you just sort of have a read as to what's going on in here, that'll explain your little exploration there. Cool. All right, that was a fun little journey. Was there
Yeah,
anything
sorry
left in? No, it's fine.
sorry
These
about
are
that
good
time.
questions because like at least these are reasonably at least the first two were doable purely methods. This one you kind of had to know a bit of spesh to do for it. And so yeah, definitely worth having a look at those in particular. But otherwise, yeah, cool. Let's return to exam solutions. Oh, I guess exams, and we'll uncover the solutions as we go. Cool. Let me pop those back in the chat as I eventually find them. Yeah, this is the one. Cool. It's a context for this one. But the overall questions that get asked after you understand the context aren't so bad. So you've basically got the river modeled by two separate circular functions, one for the top boundary, one for the bottom boundary.
Is it 10 meters?
Yeah, yeah, it's just going to be 10 meters. Um, Depends on how you went about that. Maybe you just looked at the difference between the vertical translations, probably the fastest way. Was that more or less what you did?
Um, like I looked at this first, but just to be sure, I put them into the CAS and then define them and subtracted when f of 50 minus h of 50.
F50 minus H50. Yeah, okay, cool. So you did it specifically at the 50 spot as well. Yeah, easy. Nothing too crazy. Swimmer swims east from point P. Find distance in meters. Swimmer needs to swim to hit the north bank. So you're at some point P. You're swimming east, which is right. You can imagine if you're moving directly right, you will hit that bank at some spot.
Is the does the swimmer have to swim 67 meters?
67 meters seems a bit much. Um, 67 meters. Yeah, okay. Where did 67 come from? I'll give you one hint, which is this is to scale. So you got from 50 to 100 here. You're starting at P. 67 would push it. Oh, you probably solved the second intercept then. You
Chris, is it
probably
17?
17 should be a fraction.
Yeah, like 16.66 recurring.
Oh, yeah,
16.
yeah. Okay, cool. Um, it doesn't say it around in this one, so you do want to give it exact. But yeah, um, using the 50/3 thing.
Yeah, my bad. I forgot to subtract 50 from my answer.
Oh, sure. Okay, that's why. Yeah, I thought you might have had a second spot for some reason. Yeah, so you get the yeah intercept, but yeah, you're right. Yep, that's that one. Swimmer swims the minimum distance from point P to the north bank of the river. Yeah, okay. Minimum distance now. So not necessarily in a straight line east. We're trying to get there as fast as, well, in a shorter distance as possible. Keyword minimum should be helpful here. If we think about how we find minimums or maximums of a certain quantity, therefore minimum distance, we're thinking, okay, well, we need to get an expression for distance, and then we need to use whatever techniques we know to minimize that expression. So minimizing distance. First, you need a distance equation. So you know where the point P is. You're given the coordinates of that already. What you do also know is that it has to intersect the north bank. So the north bank is the f1 function. So your other spot is going to be some point x comma f of x, specifically using the f1 function. You have your 2 points, distance equation. Now, that's going to be your Pythag, basically. If you imagine drawing a perpendicular line off of F2, you should hit F1 at the minimum distance. You're basically just using a hypotenuse, right? And so if it helps to draw the triangle out, then by all means do that. If you already know the distance equation, just use that instead. Should come out to look like that. Square root of the difference of x values squared plus difference of y values squared. That gets you your distance equation. I know it does say it on the screen, but for the next step anyway. Then we got to figure out a way to find the minimum of that particular function. One of the approaches is described there. Not necessarily the one I'd recommend, at least not in terms of speed anyway. It's only slightly slower than doing other approaches. How are we going with that? Are we fully lost or still making decent progress? Okay. So we have our equation. Diff 0 is one approach. So minimum, maximum, that should be reminiscent of finding turning points. So when you hit your diff 0, maybe one of the things you're running into is infinite solutions. Maybe. I seem to have complained about it. Point is, if you are running into that sort of issue, you just limit your domain to something that's a bit sensible. So if you have a look, it's going to be somewhere from 50 to 100. If you imagine starting from P and trying to hit that F1, it's going to be somewhere in that ballpark. Oh, I've done even weirder, which is 0 to 100, but whatever. Now it's going to give you an x value. That's the x coordinate for which there is a minimum. So you then plug that back into your distance equation to get the actual minimum distance at that spot. So that's one way of doing it. The other way is fmin. Fmin gets you straight to this x coordinate. If you're Casio, it also gives you the actual minimum along with it. If you're TI Inspire, you just do this last step again, which is sub it back into the distance formula. The other approach is you just plot d of x over a useful domain, call it 50 to 100, and then just look at where's the smallest spot on it and be like, oh yeah, analyze graph tool, because you're doing it to one decimal place. So you can just use the analyze graph tool on that and just read what the minimum y value is. Fair enough. Is there anything in there worth clarifying further? If not, feel free to move on to, where are we at? D. Yeah, D. Surface area Of the section shown on page 16, I don't think I've ever seen it referred to as a page. I mean, I have, because I've seen the exam before, but I don't remember it being very often. Surface area of the section of the river. Okay, yeah, so just surface area of the river. That's a fairly standard question. See how we go. My solution's actually cut off at this stage. They are still under development.
Is it 2000 meter squares?
Possibly. I have to quickly do it. You did integral at F1, take F2?
Yeah, over 0 to 200.
Yeah, that would have been it. I just realised I haven't written all the solutions for these yet, so I'd have to pull up a different doc to validate that real quick, but sounds like what you did is fine. Integral of top, take bottom. Alright. Part E, next up. Horizontal line drawn through point P. We kind of already did something similar. The section that is south of that line, so down of it, is declared as no swimming zone. This is a very similar question to D. So I've just basically drawn it up.
Is it 1,000?
Say again?
1,000 unit square meters?
Um, 1,000's a bit off, actually. Did you just? I can actually see it as one of the exam report things. Did you just do F1 take F2 from 50 to 100?
From 50 to 150.
Did a 150? Oh yeah, sorry, double that. Yeah, okay. Um, spot a potential issue there. So there's a no swim zone, yes. If you just do
Is it because there's like part of the area where F1 is not necessarily over F2?
Yeah. Yeah, it's going to be you want to do F1 to F2 here, and then for the remaining bits, whatever those are, you want to do, what's the line? X equals, or Y equals something, Y equals 30, I think. Yeah. You want to do 30 over F2 as the main thing there. Um, so that would be your new top, Y equals 30 over F2. Because, yeah, just doing over that domain, you would have got also this stuff up here as well, which is why you're out by a little bit. Should end up being 837 correct to the nearest square meter. You basically have twice the integral of one of these bits, which would have been from 50 to, we actually found that intercept before, 203. That'll be your 30 minus the bottom, F2. And then you want to add that to your what you did before, top take bottom, but this time you're doing it from 203, 200 over 3 to whatever this other x-intercept is. Which, just looking at the answers quickly, should be 400 over 3. So yeah, if you chuck that in the CAS, let me know if that gets you 837 rounded. Starting to make more sense why it's a 3 marker. You got to find an additional x-intercept, set up your integrals properly. Yeah, lots of moving parts there.
Yeah, I got that.
You got it? Yeah, cool. Cool. All right, that's that one. And then part F. So, north bank of the river is changing over time. It's moving further north. Moving further north, but they're applying the K as a dilate factor rather than a translate. That's interesting. Okay. Find the values of K for which the distance north. Hang on. Find the values of K for which the distance north across the river, so vertical, for all parts is less than 20. So already we kind of know K equals 1 is going to be one of those values because we figured out that the distance north was always 10 for that one. At least if I remember the number correctly. K is essentially affecting the... No, it is actually touching the vertical translation as well. Because if you imagine shoving a K onto f of x, it's not just putting it at the front here, it's also applying it to everything that is f. So you're affecting your amplitude, but you're also affecting your vertical translation. Both are going to play a role there. Because amplitude is going to figure out how much it... Yeah, I can imagine both playing a role. Not that it particularly matters, you can just sort of use the CAS to sort it out using a similar method we did earlier for vertical distance.
which means if you put a multiplication factor at the front of the function,
Mhm.
won't it also apply to the y translation, like the constant?
Yeah, it should. I don't know if I made that clear enough, but yeah, when you put k times f of x, yes, you are hitting both the amplitude and the vertical translation. Yeah,
Does k have to be less than 1.5?
possibly. Let me find out. I was still just sort of bashing things out in the cas. Less than 1.5. Uh, no, not 1.5. 1.25 would be closer. The actual fraction there is looking to be. Oh, hang on, sorry. Am I looking at the right thing? Hang on. From 1 to 7 over 6 is what it should be, not inclusive of 7 over 6. What was your overall approach there?
No, that was just like a shot in the dark, to be honest.
Oh, 1.5. 1.5 because of the difference in vertical translations.
I was more so about the dilation, but then now that I look at the vertical translation, kind of makes sense why it has to be less.
Yeah. Yeah, okay. No, this is a cheeky one. Because not only do you have to create your generalized expression for the distance north between the functions, but because of that dilation factor that plays a role in the amplitude, um, what's going on there is you now have to worry about the fact that they're a bit lopsided from each other. And so if you want to make, because now basically at different points on the river, you're going to have different distances depending on what your k values are. And so what you want to do is figure out where's the absolute maximum distance, what x value maximizes that distance, and then make sure that the k you choose is less than 20 for that. So let's see what I can do to explain that. You have your h of x, create the slider for it. I've already put the k in there. And then h2. I'll set my window settings a bit. What was it supposed to be? 0 to 200 and up to 80. And what we should see is as the slider changes very clearly, that distance there is very different to that distance there. And so what you want to do is figure out, okay, where's the maximum that that's going to be? And if we change the window settings to spot it a bit easier, peaks are still going to be the place to look. And so you think, okay, cool. There's peaks at 0, there's peaks at 200. Just pick one of them. I pick 0 and make that distance less than 20. That's going to get you the 7 over 6 as the upper bound. You still want... Yeah, why do you want k equals 1? They said you also should have k is between 1 and 7 on 6. They have a specific thing for it. Yeah, okay, they already just told us. k should be greater than or equal to 1. So that's why it's going to have a lower bound of 1 there. Make enough sense? I'm happy to explain that in more detail. Sweet. Alright, take care.